Let's continue to discuss stratified sampling. This is the fourth method. This is supplementing the previous method, which is the conditioning technique, right? So let me quickly review the main idea of stratified sampling. Consider a crude Monte Carlo estimator with the objective of estimating mu, and mu is some expectation of x. The raw Monte Carlo estimator generates NID copies of x using the sample average, and n is our simulation budget. The idea of stratified sampling is the following. Consider a discrete random variable y, and this is something you want to condition on, right? You need to know the probability mass function of y, called that pi. So pi has to be given. You can't simulate. You have to know pi. And for each case where y equals yi, for each ith case, you need to be able to simulate x. So you need to be able to simulate the value of x given that y equals y. If you can do so, applying the law of total probability, the mu is equal to ex, that is equal to ex given y equals yi multiplied by probability, y equals y. So this is simply the law of total probability, the conditional expectation formula. So what can we do about here? Okay, what can we do about it? Here is the procedure to estimate. So in order to estimate mu, we have to estimate each term here, which is indexed by I. Later, we group them together, multiply by pi, and sum up. We're good, right? So how to estimate ex given y equals y? Suppose we can do that. Suppose we allocate a subset of our overall simulation budget n, call that ni. So ni is n times pi, and n is large, p is a probability. So assuming that n times pi is integer valued, and n times pi is really large. So consider ID copies, NIID copies of x given y equals y. Take an average of them, summing up, divided by ni, which is equal to n times pi. You get, this is your estimator for the expectation of x given y equals y. All you need to do here is that consider the weighted sum of all these estimators, each of which multiplied by pi and sum up. This calligraphic E is our stratified sampling estimator. Very simple. It's easy to show. This calligraphic E has the same expectation of mu. Okay? So it's an unbiased estimator. And one quick remark here is that the total simulation budget, that is the total number of generated samples, is remained the same. We're not increasing a simulation budget. This is the same as simulation budget. Okay? It's just we're not using n copies to simulate an unconditional x. We use conditional x, and we allocate some budget for each case. So let's try to argue that why this this stratified sampling estimator can achieve a much smaller variance. Right? Let's compute its variance. But before that, let me compute the variance of this guy. This guy first. So variance of xi bar is equal to whatever coefficient in front of it squared times the variance of the summation, which gives me np times x, variance of x, divided by np squared gives me 1 np. So the variance of xi bar is equal to the conditional variance given y equals yi divided by npi. Because each case is considered, generated independently, the variance of the overall stratified sampling estimator, the variance of the calligraphic E, is equal to the variance of the sum. So we have independence, so we interchange sum with the variance. So variance of sum equals the sum of variance, and the variance of each term equals p squared times the variance of each term. So plug this into here. We cancel out the npi with the pi squared. Here we have a pi over n. That's this, right? Okay. Factor out the 1 over n, put it in outside the summation. We have conditional variance times pi, which is the probability mass of y at small y. What do we have here? This is our g function as a function of yi, and this is just an expectation of the g of big Y, or the expectation of the conditional variance. So what have we done, right? Recall that the conditional variance formula says the variance of x is equal to e of conditional variance plus variance of conditional e. This is only just one term of this. This is just this term. If you divide n on both sides, you get the variance of the stratified sampling estimator is equal to 1 over n times the variance of x, which is the raw estimator, considering the simulation budget of n, right? If you have a simulation budget of n, then this is the variance of the raw Monte Carlo estimator, and we have achieved some variance reduction because we removed this part. This part that we removed now is exactly the variance of the conditioning estimator which we introduced earlier, right? So technique 3 and technique 4, they aim to remove different parts of the raw Monte Carlo estimator's variance. Okay? So obviously this is bigger, this is smaller than this, because this is equal to this guy minus a positive quantity. Good, right? So we eliminate this part from the conditional variance formula. Alright, so this is done by assuming that the allocation is proportional to the probability. Right? Basically, I have an overall simulation budget n. I'm allocating ni, which is n times pi, to case I. It is optimal. Right? It is optimal. Can we do better? This is at least what we can do. Can we do better than this? Okay. So we have applied the so-called proportional satisfied the proportional stratified sampling estimator (PSS), meaning we allocate n times pi to each case. We can do better. Let's solve an optimization problem for the optimal n1, n2. We call them n star. Right? Stratified sampling estimator has this format. It has variance equals this, right? Okay. So if ni is equal to n times pi, we cancel all the pi and we get what we get from the previous page. Let's try not to cancel this. Let's just say this ni is something you can control, with a constraint which says ni sum up to n, right? Okay. First, do a pilot simulation to estimate the unknown parameter. This. So treat the variance of x given y equals I, some kind of given parameter. So do a pilot simulation to study that, to estimate it. Next, our objective here is to minimize this quantity, which is the overall variance, with the decision variables being n1 to nk, assuming cases, subject to a constraint, a budget constraint, right? Ni sum up to n. Right? We're solving an optimal allocation problem. Right? Before, the proportional allocation of an ni is just one case, right? We don't know if that's optimal, right? Of course, here you can see that the SI square is given as a parameter. This is estimated in the preparation phase. The pilot study estimated this, right? So we estimate this using our pilot study, so we can treat this part as a given parameter. So using very simple Lagrange multiplier based optimization technique, we're able to solve this optimization problem. This is just a quadratic function, right? I mean, this is not a quadratic function, but it's not hard to solve. So using simple Lagrange multiplier based optimization technique, we can compute the optimizers, which gives us the minimum variance. So the optimizer has this format. Ni star is equal to n, which is the overall budget, times the proportion. And the proportion is equal to pi times the standard deviation of the ISE case divided by the summation of it. Okay? And if you do that, the minimum variance of our estimator can be even smaller. This is even smaller than the one we gave on the previous page. So let me give you some intuition about this result. Okay? This result says that you sample more often from the important region, important case, here we call it stratum, stratum can be 1, can be 2, can be k. Which one is important, right? It's proportional to the probability, and it's also proportional to the standard deviation. So let's just say this conditional variance is identical across all I. Then this degenerates to the proportional stratified sampling, right? So if SI is the same, then you cancel out the SI, you have PI over 1, and that's the proportional stratified sampling. But in general, this is the optimal. This is better, right? So this variance saving we showed earlier is sort of a minimum reduction that we can achieve. We can do better than this if we want to. Okay. So, right, if the variance are the same, PSS, right? PSS is what? Proportional stratified sampling. Okay. Before I give you any example, let me try to compare stratified sampling with the use of conditioning. Okay. I mean, we always compare it to existing method. The general scheme of conditional simulation of X via another random variable Y involves 2 steps. Step 1, observe simulated value of Y, so basically simulate Y. Based on the value of Y that you observe, simulate X, right? Okay. The intuition of stratified sampling is the following. This technique removes additional variance involved in simulation Y. For instance, if X is the total sales of a shop, right, and X is equal to summation of the purchases, and Y is the total number of arrival of customers, right? You simulate how many customers you have, then you simulate additional variance sources such as Xi, you get X, right? So usually conditional simulation involves 2 steps if you condition on a random variable Y. Okay. So if you do that, your variability comes from 2 parts. The variability in the simulation of Y and the variability of the simulation beyond Y. Because given Y is still variable, right? So it's a sort of a summation of the 2 pieces. Stratified sampling removes the additional variance involved in simulation of Y. Why? Because you never simulate Y. You only simulate X given Y equals some Yi. Since you don't simulate Y, you don't have the variance from Y. Okay? So, of course, why don't we simulate Y, right? We know exactly its behavior of Y because we have the PI. PI is equal to Y equals Y. The probability of Y equals Y, right? Step 1, we simulate the conditional expectation of X given Y equals Y, then we compute the expectation of X by averaging Y. Here is the computation, not simulation. We don't need simulation to give a final output. So the variance reduction, the variance saving per run is this. It is effective, this technique, stratified sampling, is effective if this piece is big. Because this is how much we saved, right? Meaning, when the stratified variable Y accounts for a large fraction of the variance of X, then we save a lot of variances. Because see, this part is the variability comes from the Y, right? It's the variance of a function of Y, a g of Y. If Y is very variable, this variance will be big, right? So if Y accounts for a large fraction of the variance, let's say, using the sales model as an example, this Y is the total number of customers that arrive in a day. Then if that thing is very variable, then this technique may work. The conditioning, right? Let's compare with the previous method. Okay. The intuition of conditioning, which is method 3, is the elimination of additional variance involved in simulation X given Y. Why is that, right? When you apply technique 3, the conditioning technique, you simulate a Y, so you do have variance coming from Y, but you never simulate X, right? Because Ex given Y is a G function of Y. So you eliminate the additional variance involved in simulation X when Y is given. So you eliminate the different pieces, right? So step 1, observe simulated value of Y. So you simulate, then you have variability. Second, compute, not simulate, the conditional expectation of X given Y, because you have this G function here. So whenever you have a function, you can compute, you don't have to get repeated, You don't have to repeatedly get random outcome. You save the variance, right? So the variance saving per run is the opposite, the other part, the expectation of conditional variance. So you can compare with this. This is the variance of E, this is E of variance. It is effective when this peak is big. When is it big? It's big when X still has a large variance, even given Y. See, this thing is the variance of X given Y. So if X is very variable, even when Y is fixed, then this piece will be big. So these two supplement each other. Let's further compare stratified sampling with the control variate, which is method 2. So we sort of compare all of them, right? We compare method 1 and 2, 2 and 3, 3 and 2, 3 and 4, right? So here is 4 versus 2. Both approaches requires a Y as a candidate conditioning variable that should be strongly correlated with X, right? When we talk about control variate, we want Y to be related to X. Negative, positive, doesn't matter, okay? The variance of the stratified sampling estimator is this. This is something we just showed. And the variance of the control variate estimator is this. If you are able to choose the optimal C star, right? The C star have to be optimally chosen, okay? Let's compare the two. Which one's bigger? Alright, here's the result. Stratifying in Y always has a smaller variance than using Y as a control variate. Meaning, this guy is less than this guy in general. The variance of the stratified sampling estimator is smaller than the variance of the control variate estimator, even if you choose the optimal C star here. You never beat this. Here's the proof. First, take a look at the covariance between X and Y, because you want the covariance to be non-trivial, non-zero, right? So the covariance is equal to EXY minus EX times EY.